Hi, folks. Welcome back to Chapter 3, Mendelian Inheritance. This is the statistical portion of Chapter 3. I cut it into two, divided into two lectures because I wanted to teach you about the genetics and what Mendel did, what Gregor Mendel did, and why it was so significant with him not knowing that DNA was the genetic material. And now I want to come back to it and show you the math, because really he was he was a mathematician. And the reason why he came up with his postulates and concluded what he concluded is because of the math that was in front of him. So now we have to talk about what he was looking at mathematically. By the way, you're going to use these tools the rest of the semester. So please don't run from this math. You're not going to be able to run from them. You can't hide from it. They're used the whole semester. We will define probability. We write probabilities like this. What's the probability of A being whatever event you're talking about. We can write conditional probabilities. We'll say what's the probability of A given B, like what's the probability of having a heart attack A if you smoke B, something like that. Conditional probabilities will be the future. We won't talk about them today. Everything we talk about today will be independent and mainly unordered events, although I'll talk about ordered events just a little bit. So independent, unordered events. So that's mainly what we're talking about here today. All right, we'll predict the outcome of mating crosses. So these are mating crosses using some of our tools, our probability tools. And then we'll evaluate an hypothesis. We'll evaluate our data, really. I mean, you do have a hypothesis. You have a hypothesis, a null hypothesis. But we're going to evaluate our data because, if I say you're supposed to get a 3-to-1 ratio or a 9-to-3 to 3-to-1 ratio, if I say that and you have 2.9 to 1.1, I mean, is that a 3-to-1 ratio? Is it close enough? I mean, what do you think? Intuitively, you would probably say, yeah, that's 3-to-1. But maybe intuitively you wouldn't know if this was 3-to-1. What if I said it was 3.9 to 0.6? Now, actually, maybe intuitively you would say that's not. So let me get a little bit closer and see if you are questioning yourself. Is that 3-to-1? And the answer is I actually don't know. I'd have to plug it in and see. But the answer to that is we have statistical tools to analyze variances in numbers to see if they are basically the same, if they are insignificantly different. Maybe 3.9 is insignificantly different than 3, and maybe 0.75 is insignificantly different than 1. I have a feeling that this would be significantly different, but I'm not gonna, I don't know. Not off the top of my head. All right, so we'll talk about tools to look at differences in our numbers to see if they're significantly different. We'll start here. So you learned about Reginald Punnett and the Punnett square last lecture. But what I want you to do now is start thinking about, yes, this is a zygote, and it's homozygous dominant. So you know that. All right. But I want you to start thinking like this. The genotypic ratio for homozygous dominant offspring for this monohybrid cross, this is the mom, and this is the dad, is 1/4 or 25%. The genotypic ratio of my heterozygotes is 1/4 plus 1/4, which equals 1/2. I actually have 50% heterozygotes. I just highlighted them in red. Because I have two ways to being a heterozygote. I can be a heterozygote where the big T comes from the dad, or I can be a heterozygote where the big T comes from the mom. And really what I'm really saying is order doesn't matter. What I'm really saying is 1/2 of my babies are big T, little t. It doesn't matter if I write it little t, big T, or big T, little t. These are the same. Now, is that always true? No, that's not always true. Sometimes where the gene comes from matters. Example, there's a couple diseases, Prader-Willi and Engelmann's. This matters. Whoops, started writing the same darn thing. It matters who you inherited the gene from. It's the same genetic lesion, Angelman syndrome and Prader-Willi syndrome. Same genetic lesion. It depends on who you inherited from. So does order matter? Typically not. Typically we're talking about, and especially today, we're talking about unordered events. But we will break that rule in the future. And of course, my homozygous recessive genotype frequency is 25% or 1/4. Now let's talk about phenotype frequencies. How many tall plants do I have here? 3/4 are tall. 1/4 are dwarfs or short. So you can see there's a difference between genotype frequencies and phenotype frequencies. And you have to look at what you're doing and be able to calculate them. And you have to be able to apply that. Because if I say to you, I had 1,000 offspring, how many are tall? You have to be able to say that 750 out of 1,000 is your 3/4. Now, I hope that that's simple for you, but if it's not, make sure you get there. Make sure that you're there with me when we talk about this. All right. And when we do Hardy-Weinberg, we'll come back to this. All right. Let's do some hard stuff. It's not really hard. This is a trihybrid cross. What we're really crossing is a parent. Both parents are heterozygous for everything. Big T, big R, big Y, little y. Mating with big T, big R, big Y, little y. And how do I know that? Look at the parents. Big T, big R, big Y, little y. Big T, big R, big Y, little y. Those are the gametes the parents can make because that's what the parents are. Remember, the parents has to be big T to be able to make sperm that is either big T or little t. I don't know why that keeps doing that. All right, let's do a problem right here. What's the probability? What's the probability of 100% non-parental? Well, that's probably the hardest question I could ask you in here. First of all, you have to know what non-parental means. Well, my parents are all tall. My parents all produce round seeds, and my parents all produce yellow seeds. That's who my parents are. All right. So who's non-parental? Well, that's a plant that's short, a dwarf, produces wrinkled green seeds. So what's the probability of having a 100% non-parental baby? Well, it's 1/4 chance of being a dwarf plant times 1/4 chance of producing wrinkled seeds times 1/4 chance of producing green seeds. Now remember, these are independent events. There's nothing about the color or texture of the seeds that affects the height. There's nothing about the height that affects the color or texture of the seeds. So these are independent events. So the frequency there, the probability there, is 1/64. And that equals, if you want to know a percentage, 1 divided by 64 equals 0.015625. 0.015625. 0.015625. And what that is 1.5%. So 1.5% chance of having an offspring that is a short offspring that produces green wrinkled seeds. Well, what's the probability of having 100% parental? What's the probability of being parental? Having an offspring that looks like the parents. And that equals 3/4 of, my parents are all tall, round, and yellow. So 3/4 of the time, you're going to be tall, make a tall kid. 3/4 of the time, you're going to have a kid that produces round seeds. And 3/4 of the time, you're going to have a kid that produces yellow seeds. And 3 times 3 is 9 times 3 is 27. And that's 64. And that's like 41%. Let me just do it for you. I don't know exactly. 27 divided by 64, 42%. That's 0.421875. 0.421875. So that's 42. Whoops, that's not a decimal. 42%. I rounded. So you can see those probabilities there. Okay. All we're really doing is applying product rules and sum rules to the random mating and the biological events of mating crosses. All right, so what does that mean? Well, when you say what's the probability of two independent events both happening, what's the probability of A and B, or you could say the probability of A, or because we're flipping coins, what's the probability of heads and heads? What you're saying is, what's the probability of having heads from one coin times the probability of having heads from the other coin? So the overall probability in flipping two coins and getting two heads is the probability of getting one heads times the probability of getting the other heads. The answer there is when my dad flips the coin, because here's my dad flipping a coin, in 1/2 of the time he gets heads, all right, times the probability of when my mom flips the coin, moms produce eggs, and here's my mom's heads, 0.5, and that equals 0.25. So what's the probability of getting two heads? 0.25 or 1/4. 25% of the time I get two heads. All right? That's the product rule. The product rule says that the probability of two independent events happening simultaneously is the product of their individual probabilities. That's basically, I mean, read the product rule in your book, but that's basically what it says. All right, let's talk about the sum rule. What if I said, what's the probability of HT or TH? Order doesn't matter. What's the probability of HT or TH? All right, so that's going to be the probability of HT plus the probability of TH. All right. So what is the probability of having a heads or a tail? Well, I actually can take that down in the product rule, and I can say that's the probability of heads times the probability of tails plus the probability of tails times the probability of heads. So you can use both product and sum rule here. What's the probability of having a heads from your dad? 0.5. What's the probability of having tails from your dad? 0.5. Plus, that'd be tails from your mom. What's the probability of heads from your dad and tails from your mom? I got to keep track of that. Plus the probability of tails from your dad and heads from your mom. So this is 0.25 plus 0.25. And that equals 1/2. And if you look at this, it's 1/4 plus 1/4. And the reason being is because it doesn't matter who gave the head and who gave the tail. It doesn't matter if you're TH or HT, they're the same. You still have two coins in front of you where you have a head and a tail. So you use the sum rule to solve that problem. So that's the product rule and the sum rule in a nutshell. I think that's probably pretty straightforward for you. All right, let's do a real problem, not a coin flipping problem. What's the probability that two carriers of congenital analgesia will have a diseased child? Now, first of all, congenital analgesia means you don't feel pain. Now, all that glitters is not gold. This is not a good disease. You have to be checked over head to tail several times a day because, you could go into the house and your eyeball could be hanging out of your head and you don't know it because you don't feel the pain. So you're always being checked over and looking for broken bones and bruises and a finger that's hanging off by a thread and an eyeball sticking out of your head. So this is not a good disease to have. But let's do the math here. First of all, what's a carrier? Well, a carrier are two individuals that carry the disease gene but don't have the disease. Remember when I put a line over a letter, it means it's the small letter. And that's from blood bank. Remember I told you first lecture, that's an old throwback from my blood bank days when you can't afford to make a mistake. So some letters you can't tell. Is that a small S or a big S? You don't know? It's small. Well, see, you didn't know. You probably just going to say it's big. You were going to say that's a big S because you thought I was going to go like that. But I didn't. I went bigger on you. So what you do in blood bank is you put a line over the small letter. So a carrier is carrying one lesioned allele, one diseased allele, but it has a normal gene, so the carrier is not diseased themselves. So what I'm really asking is, what's the probability that two heterozygotes have a diseased child? That's what I'm really asking. And of course, you can see right now that it's 1/4. I'm sure you could see it already. This is my diseased child right there. It's 1/4, 25%. I didn't have to do it that way. I could have gone like this. I got a heterozygote mating with a heterozygote. 50% of the time I'm going to get a little p, times 50% of the time I'm going to get a little p. And that equals 0.25% of the time I get little p, little p. What's the probability that two congenital analgesia carriers have an analgesia carrier? And the answer is 50% of the time. It's 25% of the time I get a carrier where the mom gives the disease gene, and 25% of the time I get a carrier where the dad gives the disease gene, and 1/4 plus 1/4 is 1/2. It's actually 2/4 if you're not. Okay, I don't want to offend anybody, but I also don't want to skip a step where you're spending 10, 15, 20 minutes, 2 hours, whatever, saying, how the heck did he get that? So 1/4 plus 1/4 equals 2/4. 2/4 is 1/2. All right. So that's a probability problem. Here's a question. What from a cross between these two? I'm going to rewrite it because I need it down here for me. So here's a cross. What is the probability that an offspring will have this genotype? I won't have to rewrite that. No problem. I need a big A from both parents. 50% of the time I get a big A from my dad, and 50% of the time I get a big A from my mom. So what percent of the time do I have a child that's big A, big A? 0.25% of the time. 0.5 times 0.5 is 0.25. So that's 0.5 times 0.5. All right. Now I want a little b, little b. Well, 50% of the time I get a little b from my dad, and 100% of the time I get a little b from my mom. And 1 times 0.5 is 0.5. So 50% of the time I'll have a little b in my baby. So that is 1 times 0.5. And what percentage of the time am I big C, little c? See that little c right there? Big C, little c. Well, 100% of the time I get a big C from my dad, and 50% of the time I get a little c from my mom. So 1 times 0.5 is 0.5, and that's 1 times 0.5. So my answer is going to be 0.25 times 0.5 times 0.5. Or you can say it's 0.25 times 0.25, because 0.5 times 0.5 is 0.25. So 0.5 times 0.5, whoops, 0.5 times 0.5, oh, I already did that. 0.25 times 0.25 equals 0.0625. 0.0625. And that means 6.25% of the time I'm going to have that genotype from that mating. All right. All right. Now represents, okay, so now this is a set of unordered events. Now this is going to be a little bit harder for you right here. But if I say we have two heterozygote brown-eyed people, so here's a brown-eyed person, dad, mating with a brown-eyed mom, and here's your babies. But look what I asked. I said, what's the probability that two of 5 children have blue eyes. And it doesn't have to be the first or the second. It doesn't have to be 1 or 2. It doesn't have to be 2 or 3. It doesn't have to be 1 or 3. It doesn't have to be 2 or 4. It doesn't have to be 1 or 4. It doesn't have to be 3 or 4. It can be any 2 of the 5 kids. So it doesn't matter. They're unordered events. That's what it's doing. Well, what we're really saying is we're starting to use the binomial theorem. That's what we're doing. And with the binomial theorem, how it's written is this. The probability of having 2 out of 5 equals, and here's how we write it. We say 5 choose 2, and I'll tell you what that means in a second, times the probability of having a, what am I looking for, blue-eyed? Yeah, probability of blue eyes times the probability of brown eyes, or what I'm going to say here is n minus x. All right, so yeah, I think I just jumped ahead a little bit. So first of all, P is the probability, overall probability of unordered events, unordered events. All right, and that's 2 blue-eyed out of 5 total children. Probability of unordered events. When I say 5 choose 2, so when I say 5 choose 2, so it's 5 total children. N equals 5. So N equals the number of events. You're going to say, you're calling my kid an event? Oh, wasn't it? And X in this case, sometimes it's K. I'll use X because I already started using it. X equals 2, and X is the subset of those events. Subset. Or your blue-eyed kids. Blue-eyed. So N is the number of events. X is the subset of events that I'm looking for. How we write it is 5 choose 2. And P is the probability of X happening. That's the probability of X. I actually don't even have to write it. Yeah, I'll write it that way. That's the probability that you get blue eyes. Probability of X. So when I say P raised to the X, that means, well, how many blue-eyed kids do I want? P times P, because I want two of them. I mean, if I wanted 3 blue-eyed kids, it would be P to the third. But then this would be 5 choose 3 and 3, etc. So that's the probability of your event. And then we call that the probability of success. That's what we call that. And I'm not making a social statement here. Blue eyes is not successful and brown eyes a failure. But we always say this is the success. Sometimes people use K right there. So your math teacher might use K there. Tell them quit it. No, usually I have actually seen K. I don't know why I chose X today. I just did. And then Q is your failure. Q is the probability of failure. Or you could say probability of not X. Probability of failure or not X. So, and what that is instead of using another variable like Y, I could use Y, I haven't used it yet. What's left over is the total minus X. But instead of introducing another variable like Q to the Y, I just say P to the X times Q raised to the N minus X. So that's what we have there. This is called the binomial distribution, and we're going to talk about this. This right here is the binomial expansion. We're going to talk about that right now. And you use this to solve questions like what we have here, which we'll eventually solve, but I have to talk about what 5 choose 2 means. That's what I have to talk about. All right, so let me talk about when order matters and when order doesn't matter. Well, when order matters, that's called a permutation. All right, that's when order matters. Let me just do an example, and an example will explain it. What happens if I said you had 3 events and you wanted the permutations of those taken, You have 3 total events, and you want to take them 3 ways. How many different permutations do I have? So your 3 events are A, B, and C. All right. Well, I could have A, B, C. I could have A, C, B, and I could have, oh, and by the way, yeah, that's it. All right. I could have B, A, C, and I could have B, C, A. I could have C, A, B, and I could have C, B, A. Now look what I did. All I did was I started with A in the first position. I put the B and the C in the only order they could be in. BC, CB. Then I put B in the first position. And I did my other 2 variables in the only other 2 orders they could be, A and C and A. And then I put C in the first position, and I put A and B in the only other 2 orders they could be. So the answer to this permutation is 6. Because 1, 2, 3, 4, 5, 6. Now, with our problems, order doesn't matter. And if order doesn't matter, aren't all of these the same? ABC is ABC. These are all the same if order doesn't matter. And if order doesn't matter, then this is 1. The number of combinations, if it doesn't matter what order this is in, is 1. So, in fact, the way you write combination is you have 3 choose 3, and that would equal 1. And this is showing you 3 chooses 3. I have three trials, 3 events, and I'm choosing them and order doesn't matter. Well, if order doesn't matter, it doesn't matter if I'm ABC or ACB or BAC or BCA or CAB or CBA. It doesn't matter. So you can see that a permutation where order matters is different than a combination where order does not matter. By the way, what do you put on your locker? Combination lock. You put a combination lock on your locker. Your combination is 12, 15, 40. Well, shouldn't we call that a permutation lock? And I would say yes, because do you think if you put 15, 40, 12 into your lock, it would open? I would say no. So your combination lock is a permutation lock. I would go get my money back. They lied to you. All right, so a permutation. Order matters. You can see that right there. Oh, I shouldn't erase the word permutation because I wanted to show you something. Well, what a permutation is this. Let me write that again. A permutation, let's just do 3 events, choose 3. A permutation is written like this: n factorial over n minus x factorial. All right, now let me put these back here. ABC, ACB, BAC, BCA, CAB, CBA. All right, so I got my 6 events back there, I hope. Yes, I do. All right, so what is this? Well, what I have here is I have, well, I never explained, I've never explained factorials to you yet. What a factorial means is if you take any number, like let's say you take 6 factorial, it really means 6 times 5 times 4 times 3 times 2 times 1. That's what 6 factorial means. All right, so 3 factorial is going to be 3 times 2 times 1. That's what 3 factorial means. So I hope by not explaining factorials first, I hope that didn't screw you up. All right. This is the formula for permutations. N factorial over n minus x factorial. In permutations, order matters. I want you to remember that order matters. Why do... no, that doesn't matter. I'm not going to explain that. Okay, so that's a permutation. Well, what's a combination? Well, a combination is just a permutation, but you divide out things that are the same. All right. Oh, what the heck does that mean? Well, AB, well, let's do it a different way. Let's do 3 choose 2 because it'll show it because the combination for that is 1. I want to show you a combination that's not 1. What if I did a permutation where I had 3 events, choose 2? All right, so I have A, B, and C, but I'm only taking them 2 at a time, right? So I have AB, I have AC. Whoops, I actually don't want to do it that way because it's going to show you the factorial. I have AB, and I have, yeah, I do want to do it that way, AC, AC. And then I have BA, and then I have BC. And then I have CA and CB. CA and CB. Yeah, that works. That works perfect. Now, this permutation, 3 events, choose 2, ABC, that's going to be 3 factorial over 3 minus 2 factorial. Remember, it's n factorial over n minus x factorial. That's a permutation. Well, 3 factorial is 3 times 2 times 1, which equals 6. And 3 minus 2 is 1, and 1 factorial is 1, and that equals 6. Do I have 6 events? Yep, 1, 2, 3, 4, 5, 6. All right. But if this were a combination, wouldn't these be the same? And if this were a combination, wouldn't these be the same? And this were a combination, wouldn't these be the same? And my answer is, yeah, my triangles are the same. Order doesn't matter. If it were a combination. So my triangles would be the same. My circles would be the same. My rectangles would be the same if this were a combination. What did I just erase? I didn't mean to. ABBA. ABBA. All right. So what a combination is 3 choose 2. That equals n factorial. Let me rewrite what the permutation equals. Permutation is n factorial over n minus x factorial. That's what a permutation is. But what a combination is n factorial over n minus x factorial times x factorial. All right, that's what a combination is. Well, what's the difference? This guy right here is the difference. That's the difference. So why do I do that x factorial? Because I have to divide by a correction factor for my groupings that are possible. That's what I have to divide by. And I can divide right here. Right here, A and B are not different. These are not different. A and C and A are not different. And B and C and B are not different. So to correct for these groupings that aren't different in combinations but are different in permutations, I divide by my correction factor right there. So that's and by the way, let me change this. 3 choose 2 is not n factorial n minus x. This is n choose x. N choose x is n factorial over n minus x factorial divided by x factorial. And that's a combination. And by the way, it's sometimes written like this. It's sometimes n choose x with a c right there, where permutations is a p right there. So that's how you write that. And by the way, sometimes it's k. Matter of fact, I'm more used to k than I am the x, but it doesn't really matter. And in this case, that would be n factorial over n minus k factorial times k factorial. All right, so don't get all confused about using different variables. All right, now we got to go back to our binomial distribution. Matter of fact, I will just do it right from here. All right, so what do we have? 5 kids, And we want to know what's the probability. 5 kids. Let me go back. I don't remember. We have, yep, BB. Okay. 2 monohybrid cross. 5 children. We want to know the probability of 2 having blue eyes. All right. So here's our monohybrid cross. There's my blue-eyed kid. So P equals 0.25. Probability of having a blue-eyed kid is 0.25. That's the probability of having a blue-eyed kid. Q is 1 minus 0.25, or 0.75. P plus Q always has to equal 1. Okay, those probabilities always have to equal 1. Probability of success, blue eye. Probability of failure, brown eye. All right. So P equals 0.25. Q equals 0.75. All right. Now, what I want to do, what the question is what's the probability? What's the probability of blue? Or I could say little b. What's the probability of that? If I have 5 kids, what's the probability of 2 kids having blue eyes? So 5 choose 2. Probability raised to the x, which is 2, times q raised to the 5 minus 2. I'll actually leave that in there for now. N minus x, which is 5 minus 2. Let me rewrite that. What's the probability? 5 choose 2. 0.5 squared. Wait, not 0.5, 0.25. Geez, Kiggins, you're going to confuse everybody. The probability of having a blue-eyed child is 0.25. 0.25 squared. Zero 0.25 squared times Q, which is probability of failure, 0.75 to the third, 5 minus 2. I hope I can just put 3 there now. 5 minus 2, because n minus 2 is 3. Now, let me just show you that. How come my 0.25 is squared? Because there's my little b, and it's only 0.25, because I want to have 2 of them. So it's 0.25 times 0.25, or 0.25 squared. How come my 0.75 is cubed? Because I have 3/4 that are brown-eyed, that are Q. 3/4 of my kids, 0.75% of them are brown-eyed. So it's 0.75 cubed. And why cubed? Well, here's the 3 right there. All right. There's 3, and I want 2 of these guys. So that's why I have that. So the probability of blue equals 5 choose 2. And let me just do 0.25 times 0.25. 0.25 squared equals 0.0625 times 0.0625 times, let me do 0.75 cubed, and find your x to the y on your calculator. That's what I would do. So if you find your x to the y, you don't have to sit there and do 0.75 times 0.75 times 0.75. You just do 0.75 x to the y 3, and you hit it, and what you get is 0.421875. 0.421875. All right. I want to multiply these 2 together just so I have one number there, and I'm going to go to the next page and finish this off. So 0.421875 times 0.0625, that equals 0.0263, blah, blah, blah. I'm going to round that, folks. I'm going to round that to I'm going to truncate it, actually. No, I'll round it to 0.0264. So the probability of blue equals 5 choose 2 times 0.0264. 0.0264. I rounded. All right, now let me write this again. 0.264. 0.264. 0.264. Remember, it's two blue eyes, though. Now, you already know it's two blue eyes because I choose 5, choose 2. Blue equals 5, choose 2. Oh, I forgot. 0.0624. 0.0264. 0.0264. 0.0264. Right there. All right. What is 5 choose 2? Well, we already went through that. Remember, what 5 choose 2 really means, what n choose x really means, is n factorial over n minus x factorial times x factorial. So what 5 choose 2 means is 5 factorial over 5 minus 2 factorial times 2 factorial. What that is 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. I wrote it like that on purpose. Times 2 times 1. These cancel. So what that equals is 20 over 2. 2 times 1 is 2, which equals, whoops, wow, it's definitely not 20 over 20. 20 over 2, which equals 10 times 0.0264. And that equals 0.264. So the probability of me having 2 blue-eyed kids out of 5 from a monohybrid cross is 0.264 or 26.4% chance. 26.4% chance. Whew. Boom. There you go. Now, I actually don't know what your book says. I hope I did that right. So that's the binomial distribution. All right. Good. So why do we have this binomial distribution? I want to show you where we're going. Because in the future, we're going to be talking about P plus Q to the N. All right. And really what this binomial expansion, the 5 choose 2, the N choose X, the N choose K, or whatever it is, it actually is an expansion of this right here. No matter what this is, it could be 3, this could be P plus Q squared. Let's just do P plus Q squared. You're going to know this. You're going to say, Kiggins, I know that. I've been foiling since I was in 8th grade, 7th grade, whenever you start to foil. First, outer, inner, last. That's how you learned it. Foil. First, P squared plus PQ plus QP plus Q squared. All right. And then you said, well, I'm going to simplify that to 2PQ because order doesn't matter. These are the same, 2PQ plus Q squared. And I'm going to say, yeah, you got it. That's how you expand that binomial right there. But what if that was P plus Q even to the third? What if that was that? Well, you could still do that. I'm positive you still could do that. But let's go down and talk about it a little bit so you see why we use the combinatorial property. All right. So what does P plus Q squared equal? It equals P plus Q times, or cubed, I mean, P plus Q times P plus Q. So that's P plus Q squared. Now, for every single slot right here, I have 2 choices. For every term there, slot or term there, I have two choices. I have a P or Q choice there, I have a P or Q choice there, and I have a P or a Q choice there. So the total number of combinations, well, I shouldn't say it like that. The total number of terms I'm going to have are 8. 2 times 2 is 4 times 2 is 8. All right, that's the total number of terms I'm going to have. And if I do that out, I hope I can do 8 terms. I haven't done this in a while, but let's see. Well, I have P, P, P plus P, P, Q plus P, Q, P, P, Q, P plus P, Q, Q plus Q, P, P plus Q, P, Q. I'm just making sure I don't already have that one. Plus Q, Q, P. Nope, I don't have that one. Plus Q, Q, Q. I hope that's 8. 1, 2, 3, 4, 5, 6. Oh, good. I think I did it right. So this is what I could have. This P with these two P's. This P with this P, but that Q. This P with that Q, but that P. And so on and so forth. All right, so that's what I have. When I actually group these terms, I'll know if I made a mistake. But I just wanted to leave it ungrouped for a second. All right, so what do I have here? Well, I have P cubed. There's P cubed. And I have 3 P squareds. At least I should have. 1, 2. Oh yeah, I don't know why I didn't see it. Those are my P squares. So plus 3P squared Q. Oh, by the way, let me back up a little bit. Just because I'm not backing up, I'm just erasing that and giving myself some room. Just so you know, anything raised to the 0 power equals 1. All right, so 10 to the 0 equals 1. 100 to the 0 equals 1. Everything raised to the 0 power equals 1. I just want to do some housekeeping, and that's really what is the downfall here. This is P cubed Q to the 0. This is 3P squared Q to the 1. There actually is a Q there. See, PPQ, PPQ, PPQ. All right. Plus, well, there's going to be there should be 3 PQ squares. There's PQ squared. There's PQ squared. And there's PQ squared plus 3 PQ squared. And that's P to the 1. All right. P to the 1. And plus there's going to be a Q cubed. But that's really P to the 0 Q cubed. Is that the only thing I haven't done yet? I did that one in the beginning. And yep, okay, I'm done. Good, I did it right. And that's what I have. That's really my binomial expansion right there. That really is that. But I want to show you something. There's an easier way to do this. And by the way, that's not different than this, and I'll show you in a second. Holy cow, that is the same thing. All right, so it's not different. Okay. Good, I got one more. Here's an easier way to do it. This is how I remember how to do it, but see, it should be proven to you at least once. That's what should happen. All right. Yeah. Let me just write it like this though, because I wanted to show you 2 more things. I want to write P3Q to the 0. All right. 1P3Q to the 0 plus Oh, I forgot already. 3p squared q1, 3p squared, 3p squared q1 plus 3 p 3 2 p1 q squared plus 1 p0 q cubed. This is how, okay, that's right. So I want to show you a couple things here, but here's how I do it. If I have p plus q cubed, here's what I do. I put pq, I put terms pq in there, and I do one more term than my exponent. So I have my exponent's 3, I put 4 terms in there, 4 pq's. And then I start right here. I start and I say p cubed p cubed, q0. These exponents always have to equal that exponent. 3 plus 0 is 3. P squared, q1, 2 plus 1 is 3. P1, q squared, 2 plus 1 is 3. P0, q3. 3 plus 0 is 3. Notice what happened to my p's. P to the third, p to the second, p to the first, p to the 0. Notice what happened to my q's. Q to the 0, q to the 1, q to the 2, q to the 3. See the pattern? Now, what about my coefficients? These are called my binomial coefficients. Well, really what these binomial coefficients are is really this is 3 choose 0, which by the way happens to be 1. That's the coefficient. This coefficient right here, which happens to be 3, is 3 choose 1. And I'll prove to you that 3 choose 1 is 3. So 3 here is 3 choose 1. And this right here is, again, it's not 3 choose 0, but it's 3 choose 3. But 3 choose 3 is also 1. And I can prove that to you in a second. So the coefficients, my coefficients 1, 3, 3, 1, are really right here, my combinatorics. 3 choose 0, 3 choose 1, 3 choose 1, 3 choose, oh, that's 3 choose 2. I'm sorry. I'm very, very sorry. It still equals 3, which I'll prove to you, but it's 3 choose 2. It's 3 choose 2. All right. All right. You can do it like this. You can say, look at, I'm choosing 3 things total, and none of them are Q's. So all 3 are P's. I'm choosing 3 things total, and 1 of them are Q's. So 2 P's and a Q. I'm choosing 3 things total, and 2 of them are Q's. 1 P, 2 Q's. I'm choosing 3 things total, and all of them are Q's. 0 P's, 3 Q's. But there's something else you can do. You can actually get your coefficients that I have to write in these boxes. You can get it from what we call Pascal's triangle. And this is pretty darn cool, by the way. This would be 1 plus 1 is 2. So 1 plus 1 is 2, so 2 goes in the center. But what's 1 plus 2? 3. What's 2 plus 1? 3. What's 3 plus 1? 4. What's 3 plus 3? 6. What's 3 plus 3? 1. And you could keep going. Put a 1 out here. What's 4 and 1? 5. What's 4 and 6? 10. What's 6 and 4? 10. What's 4 and 1? 5. And these are actually my coefficients. These are my coefficients. All right, so this is the this is the end of the 0 coefficient. I didn't know how to say it to you. This is end of the 0, end of the 1, end of the 2. All right, so that's what they are. So all I have to do is look down at my end of the 3. Why? Because I'm p plus q to the third. I'm raised to the third exponent. This is the row I'm concerned with. 1 goes here, 3 goes here, 3 goes here, 1 goes there. 1, 3, 3, 1. Now, I think you can see that 3 choose 0. Well, let me just prove it to you. 3 choose 0. Remember what it is. It's 3 factorial over 3 minus 0 factorial divided by, or times 0 factorial. By the way, 0 factorial equals 1. Uh, just so you know, 0 factorial equals, I don't know what just happened. 0 factorial equals 1. All right, got back to normal. I don't know what just happened there. Don't ask me why 0 factorial equals 1. I asked my son one time. He said because it was convenient. He's pretty good with math. And I said, hey, Jake, I said, why the heck does 0 factorial equal 1? And he says, because it's convenient, Dad. I said, well, that's a pretty shitty, that's a pretty crappy answer, boy. And that's the answer he gave me. Anyway, 3 factorial is 3 times 2 times 1. That's 6. Over 3 minus 0 is 3. 3 factorial is 6. Times 1 is 6. 6 over 6 is 1. Let me prove to you. You guys can prove it. You don't need me to prove this stuff. So anyway, that's the binomial distribution. That's where it came from. This is called Pascal's triangle. And by the way, we use all of this to solve any unordered question in genetics. A series of events that are unordered, like what's the probability of having 2 blue-eyed kids out of 5 children from a monohybrid cross? That's what we use. I've been talking on and on. I hope that makes sense to you. If not, look at the video again. If not, email me, come see me. All right. This is the chi-square test. What the chi-square test does is it tells me if two numbers are actually different from each other. It's an analysis of variance. It's an analysis of variance. And what this is saying is it's saying I sum my terms observed minus expected squared divided by observed. So I'm going to have like a term, O minus E squared divided by E. I'm going to have another term, O minus E squared divided by E. And I'm going to have another term, O minus E squared divided by E, and I'm going to add all those together. I sum them. That's what I do, is I sum them. So that gives me a chi-squared value. And what I do is I take that chi-squared value, and let's say it's 1.9. I'm just making it up. And I look at a chart. All right, I look at a chart for my pi-squared value. And what I do is in science, I usually choose a alpha level of either 0.05 or 0.01. And what this tells me is my degree of confidence in my answer. If I have an error, if I'm accepting an error of 5%, then I'm 95% certain that my answer is correct. If I have an error of 1%, then I'm 99% certain that I'm correct. So this is my confidence level. All right, so this is this 0.05 is actually called my alpha level, but then the inverse of that, the 0.95 is my confidence level, 95% confident. All right, so I said that I had a 1.9. I just made up that number. I actually hope it doesn't come out to 1.9. You guys would think I knew. Chi-squared equals 1.9. I just made it up. So what I do is I look at my null hypothesis. I'll talk about null hypothesis in a second. And any number 7.815 or less is insignificant. Insignificant. All right. Anything greater than 7.815 is significant. Now you're going to say, why did I go with this group of 3? I'll show you in a second. Because you really do have to choose your degrees of freedom as well. But I'm just showing you that I compare my chi-square to a number here. And if my chi-squared is less than that number, then my numbers are the same. I have an insignificant difference. All right. If my number is greater than that, I reject my null hypothesis. Now, my null hypothesis is a hypothesis of no effect. So if I had a hypothesis that sulfur dioxide stunts plant growth, if that was my hypothesis, my null hypothesis wouldn't be sulfur dioxide enhances plant growth. My null hypothesis would be sulfur dioxide has no effect on plant growth. But I could reject that null hypothesis if my chi-square doesn't come out less than 7.815, which would mean sulfur dioxide does indeed stunt plant growth. So let's go through one of these. All right. What I did was a dihybrid cross. So here's what I did. I made it a heterozygote for wing straight or curly. It was a straight wing fly, but it was a heterozygote. And I made it, and it was heterozygote for a gray body, black body. It was a gray body, but it was a heterozygote, and I mated it with a straight winged gray body, likewise. Now, if you recall from the first lecture, this is going to give you a 9:3 to 3:1 ratio. I'm not going to redo the Punnett square for you, but that's what you get is a 9:3 to 3:1 ratio. All right. That means 9/16 of the babies should be straight and gray. 3/16 of the babies should be curly and gray. 3/16 of the babies should be straight and black. And 1/16 of the babies should be curly and black. That's what that means, a 9:3 to 3:1 ratio. My hypothesis is the two traits are independently assorting. My null hypothesis, H naught, is that they are linked or they're not independently assorting. Now, if they're independently assorting, I'm going to get a 9:3 to 3:1 ratio. Not independently assorting. Okay. So I got to see if I get a 9:3 to 3:1 ratio. Well, what did I observe? I observed 193 straight gray, 69, get out of there, 69 straight black, 64 curved gray, and 26 curved black. All right, that's what I observed. What did I expect? Well, I had 352 total flies times 9/16. That's what I expected there. I expected 9/16 of them to be straight gray. 9 divided by 16 is 0.5625 times 352. All right, so that's 198. I expected 198. Let me say to you again how I got that. 9 divided by 16 is 0.5625. 52 times 0.5625. And that equals 198. And I'm going to do the rest of that for the rest of these. Remember, this is 3/16. This is 3/16. This is 9/16. This is 3/16. This is 1/16. All right. So I'm going to do the rest. I'm just going to do it on my calculator. I haven't done it ahead of time, so I'm sorry I haven't done it ahead of time. But out of 352, so 3/16, 3 divided by 16 times 352, 66. And this will be 66 as well, because 3 divided by 16 times 352. And then 1 divided by 16 times 352 is 22. Now, is 22 different than 26? Is 66 different than 64, et cetera, et cetera? So now I do O minus E. And it doesn't matter if it's a negative number because I'm going to end up squaring them, all right? So 193 minus 198 is negative 5. All right. 69 minus 66 is positive 3. This is negative 2. This is negative 4. All right. Don't worry that it's negative. Square it. Negative 5 times negative 5 is 25. 3 times 3 is 9. Negative 2 times negative 2 is 4. Negative 4 times negative 4 is 16. Now I take these O minus E squared and I divide it by expected. So 25 divided by 198. 25 divided by 198 is 0.126. 0.126. I truncated Yes, I did. 9 divided by 66, 0.136. I can tell you we're going to be insignificant. These numbers are pretty small. I truncated. 4 divided by 66. Yeah, these are real small numbers, just so you know. What did I get? 0.06. And 16 divided by 22. 0.72. 0.72. All right. I truncated a lot of these, so please bear with me. Now all I got to do is do the sum of all of these. Chi-squared equals the sum of O minus E squared divided by E. So what's 0.126 plus 0.72 plus 0.136 plus 0.06? Well, let me just do it. Plus, plus, plus. That equals 1.05. Chi-squared equals 1.05. Now, what's my degrees of freedom? Can't spell. Well, what a degree of freedom is usually n, your number of groups, or your population size, minus 1. I have 4 groups here. But did I take these groups one at a time? And the answer is yes. I looked at these groups one at a time. So my degrees of freedom is 4 minus 1, which, 4 minus 1, which equals 3. Now realize the degrees of freedom, if you take them 2 at a time or 3 at a time, would have been different. Like if I have a group of 100, but I take them 4 at a time, then my degrees of freedom is not 99, but 25. Because I took them 4 at a time. So it's my n minus the number of groups how I took them. I actually don't know if I just did that math right, but if I have n equals 100 and I sample one at a time, or I look at the groups one at a time, then it's n minus 1. But it's n minus the size of group that you're looking at. So my degrees of freedom here, my freedom of rotation they call it sometimes, my degrees of freedom is 3. 4 minus 1 is 3. I have 4 groups here. So 4 groups minus 1 is 3. My degrees of freedom is 3. So now, my chi-squared is 1.05. My degrees of freedom is 3. And here's my critical value. Anything less than 7.815 at an alpha level of 0.05 is insignificant. My data suggests that I am independently assorting, because my data says that 198 is not different than 193. It says that 66 is not different than 69, so on and so forth. Whew, folks. All right, now listen. I know you're going to say, here's what you're going to say. Here's what I'm going to say to you. Quit it, you big baby. Master it. Please master it. Quit being scared. Quit hiding. And master this. You need it. You need it for the rest of this course. You need it for your life, to be quite honest. So I'm not ever doing hard math in this course. I really am not. But you're going to need this for the rest of your life, basically. You need the binomial expansion when you do calculus. Just so you know. You're going to, when you do the derivative formula, you have to expand a binomial. So you're going to say, what? No, I don't. Yeah, you do. You certainly do. So that's a derivative right there. All right. And f of x plus h, if x is n, that's going to be It's going to be f of x plus h to the n plus x to the n over h. And guess what this is? You have to expand that binomial. You have to do just what we just did. So you need binomial expansion in calculus, you need binomial expansion in genetics, you need binomial expansion in a lot of things. And the most powerful thing about binomial expansion is everything can be a binomial. Everything can be. You're going to say, no, hair color can't be. We have redheads, and we have brunettes, and we have blondes, and we have black hair, and we have blue hair. That's only your grandmother coloring her hair. Yeah, but that's all right. I could be a binomial. I can be red and not red. That's a binomial. I could be blonde and not blonde. That's a binomial. Everything can be a binomial. You need binomials for your life. All right, folks.